Hello everyone, welcome to this material characterization course organized by NPTEL. And we have been looking at some of the tutorial classes in the last 2 or 3 classes, and I have been working out some of the problems which is related to electron diffraction and how to interpret them and how to index them and so on. In the last tutorial we just looked at some of the single crystal electron diffraction pattern using one method called ratio method, where you just have electron diffraction pattern. You start with the pattern and then look at the different ratios. You make a table and then you try to find out the zone axis and so on. So, in today's tutorial class, I would like to demonstrate indexing the single crystal electron diffraction with another method called zone axis method. Here we first look at the zone axis, and from there we will look at the individual planes where it contributes to the electron diffraction spot. And we can also have a comparison at the end how it looks like and how they are related. And whichever the way you choose, the ultimately you have to arrive at the correct solution. You can see in both the cases they are same. And at the end I will also show some simple procedures to look at electron diffraction from a polycrystalline specimen. So let me straight away start with the second method called zone axis method. So what we have done is we have taken a simple electron diffraction pattern from the FCC crystal, which has got the distance in this direction is 1.10 centimeter, and this vertical distance is 0.65 centimeter, and the angle between these two directions is about 90 degree, and this is one pattern. Similar pattern we have taken for solving the indexing in the previous tutorial also. So that you can compare both the methods, how to see the solution in two different methods. So this is a single crystal electron diffraction pattern. So, now we will see how to go about it. So, before I really get into the technique, let me also draw some table where it says some symmetrical diffraction So, what I have done here is I have just put some of the symmetrical aspects of diffraction pattern of a cubic crystals. So, before you look into solving the single crystal electron diffraction pattern, you can have a reference something like this, where you have the zone axis. For example, it is 1 0 0, 1 1 0, 1 1 1 in a cubic system. Then you can look at their symmetry, whether it is a square, a rectangle or hexagonal. Then you can immediately recognize some of the indexing aspects of them. So, it is quite useful to have a table like this to compare the single crystal electron diffraction before you indexing. So, and also you can look at the aspect ratio. If it is the square pattern, then it is 1:1, and if it is rectangular, it is 1:2 square root for a BCC and simple cubic, and it is almost hexagonal for an FCC, and if it is for 1:1, it will be a equilateral. So, some of these symmetrical aspects will readily give you a clue about this kind of the origin of this electron diffraction. So, you can readily go to the reference book or any handbook where you can compare the single crystal electron diffraction pattern which is given in the for ready reference. So, that way it is easy to solve them, but in this case let us see whether it follows any of this symmetry. This particular single crystal electron diffraction pattern, since it do not follow any one of this, then we will take the other method of solving it. So what now we have to do is, since the method itself says that we will start with zone axis, we have to select some zone axis by guessing. First of all, we have to look at whether this pattern is in falling with any of this symmetry, and you also have to look at the kind of patterns. So that means the density of the spots is reasonably high, so we expect a zone axis of fairly low order. So we have to now look at the lowest zone axis what are possible. So we will start with the 1 0 0, 1 1 0, 1 1 1, 2 1 0, 2 1 1, 3 1 0, etc. And you can also look at this 2 0 0, 2 2 0, 2 2 2 and 3 0 0 and so on. And please note that in defining any of the zone axis, the 1 0 0, 2 0 0 and 3 0 0 directions are the same, since they point to the same direction. So you have to look at some of the lowest possible zone axis, and since this pattern does not fall into any of this, we cannot take this 1 0 0 because it is not falling into this any of this symmetrical or aspect ratio in the table. So what we will do is, we will select the next lowest, the first three we leave it, we will take the 2 1 0 as the zone axis as a guesswork. So what I have written here is, we have now taken the next lowest order zone axis 2 1 0. So the allowed diffraction spots must be perpendicular to this zone 2 1 0 axis. To test that, for the perpendicularity with 2 1 0, we seek the dot products that are 0. That is what the condition. The plane which is lying in any zone axis, according to the Wies zone law, all the planes should be perpendicular to this direction. Then we can say that all the planes are lying in this zone axis. So we will simply say that So now if you look at this the lowest index planes which are lying in the zone axis, we check this whether these two are in perpendicular. So they are not 0, the dot product is not 0, that means they are not lying in the zone axis, or the plane is not perpendicular to this direction. So similarly for this. On the other hand, 0, 0, 2, this is 0, that means this direction or a plane must be lying in this direction. So these two are not perpendicular, and similarly these two directions are not perpendicular, but 2, 4 bar 0 is perpendicular to 2, 1, 0. So from this we have some idea. These two cases you have, for example, this, there is a possibility that this plane and this plane can be lying in the zone. So let us see how to proceed further. So we can take this . So what is the next step? So now we have taken one zone axis and then we looked at all the possible directions or plane normals, which is dot product x is equal to 0. Then we found that this plane normal are perpendicular to 2, 1, 0. Then we can assume that these two planes, diffraction planes, appears promising because of this perpendicularity. So the next job is we have to just put these two planes in a respective distance to make sure that they are exactly lying in 2, 1, 0. So for that we have to check with the other parameter to keep these two planes in correct directions. How to check that? So that is our next step. So what I will do is, So, what we have done is the final step is to lay out the spots at the correct distances to make the diffraction pattern for the 210 FCC zone axis. So, we rearrange the camera equation RD is equal to L lambda to obtain the measured distance R of a diffraction pattern spot from the transmitted beam. That is, this distance whatever we have measured, this one and 1.10 in this the other direction, that we will put. So, if you in this equation, suppose if you know the camera constant already, then directly we can put it, but if you do not know the camera constants, since it is a constant number, you can take the ratio of these two planes and then you can try to find this distance. So, that is what we are going to do. So, the above equation shows ratio of the spot distances must equal to So, what we have done here is the equation of the camera constant shows that the ratio of the spot distance must equal to the ratio of the factors square root of h square plus k square plus s square. So, that means since we do not know the camera constants, we can adopt this method. So, in this particular case, we take the vertical distance which is 0.65 centimeter to the 002 plane from the transmitted spot, that is 000 as a reference distance. Then we can put that as the ratio of these two planes, then what we get is 1.45 centimeter. That means this is vertical distance, what you will get as an horizontal distance, that is 1.45 centimeter. But what you have to now look at it is whether this is matching with what we have originally had in the problem. It is slightly higher than the initial distance, which is 1.10. So that means this zone axis selection 210 is not correct. So far it was good, but once you want to place the two spots 002 and 2 bar 0 in a correct distance, and we are not getting the close distance what we have actually measured. So that means this particular zone axis is not the correct zone axis for this part. So this is one clear cut example of a wrong indexing. Okay, that is how it should be measured. So what we should now do, we can write so that means the 210 zone axis must be wrong. So we have to try again with something else. So how to move further? We make another guess. So we will make another guess, that is the next in the line in the original possible zone axis. After 210 it is 211. So we will take this and then try the same procedures like what we have done. So what we have done here is, since we are making another zone axis 2, 1, 1 as the new zone axis, then we need to explore all the low index planes or their plane normals perpendicular to this zone axis. So for that we have created a table, the expected diffraction, and they are all normalized with their HKL indices like this, so that you find out the cos theta value. From there you actually find the theta, that is the angle between the two planes. So it is quite straightforward. So you take this first 1, 1, 1 plane normal, and which is the dot product is 0, and then you see that cos theta is equal to 0 by square root of 18, which is nothing but the theta is 90 degree. That means these two are perpendicular to each other. So similarly you try 0, 0, 2, which is not equal to 0, and then you get you see that the planes are also not 90 degree apart, that is not perpendicular to each other. But you have 0 to 2 bar, the dot product is 0, similarly you can prove that the angle is 90 degree. So similarly 1, 1, 3 bar, these two are dot product is 0, and then you can see that angle is cos theta is 90 degree. I mean cos theta is 0 and theta is 90 degree. So like that you have 1, 3, 3 which is not perpendicular to each other, but you get a finite some angle which is other than 90 degree. So the fourth one is perpendicular to each other, so you get about 90 degree between the two planes. So like that it is a one standard way of putting in a table, so that you readily work out the planes or the plane normals which are perpendicular to this zone axis. So from now we can just move on to assigning the indices to the So now what you see from this relation, similar thing, suppose if you take from this table the first two perpendicular planes, and if we can put them in their respective distance, according to this distance is coming to 1.06 centimeter, which is very close to what we had in the measured distance, which is 1.10. So that means this calculation is correct. We can now rest assured that this zone axis is a correct zone axis. So now we can just expand this. So, once you have this the basic two planes, and then if you can expand the reciprocal lattice with the linear combination of these vectors. Suppose if you consider this as a vector and this as a vector, you can add these two to get this. Similarly, you can expand this with this. For example, you can keep on adding this with this vector and then get this. So, something like this. For example, you add these two, you get this 2 bar 2 plus 2 4, 2 plus minus 2 is equal to 0. So, similarly, you can just add these two as a linear combination, and then to get this, and you can add these two to get this similarly. So, it is a combination linear, you can just expand this whole net as much as you want, then still you will see that all the planes will lie in 2 1 1 zone axis. So, that is the solution of, or finding the indices of all this single crystal electron diffraction pattern. But what you can see here is there is you can see that your HKL, H is constant in this direction and K is delta plus 2, L is So, you can also have some idea from this basic vectors, the HKL values in this direction, that is the increment as you go from this transmitted beam to right hand side, the increment towards this direction, that is H is constant, and K, the difference is plus 2, the L is minus 2. So, which is nothing but 0 to 2 bar. Similarly, the increment along this column, you have delta is equal to minus 1, delta is equal to plus 1 in the case of K, delta is equal to plus 1 in the case of L. So, the total you will have bar 1 1 1 as an increment when you move in this direction. So, that is another way of cross check this, and though it looks little bit longer procedurally as compared to the ratio method, and both the methods are useful in indexing a single crystal pattern like this. So, finally, what we can do is we can also now show that probably you can do it as an exercise, because you can take any one of this plane and then make sure that they are all lying in this 2 1 1. That means their cross product, dot product should be 0. You can check that, and what I will like to do in the next tutorial, we will look at the polycrystalline electron diffraction pattern. You will get a ring pattern. So, I will work out the procedures how to index those polycrystalline pattern using some simple procedures, and then you can also practice for the some of the known crystal system, and then we will also compare that procedure how to apply it for the unknown crystal systems. Thank you.